Imagine you wake up, and there is nothing. No timber, no mortar, no shelter within 100 miles. Outside, the Atlantic is screaming at force 10. Wind speeds that can rip a modern steel roof from its bolts. Waves that have swallowed entire fleets. And the temperature, dropping fast. This is not a nightmare. This was every winter morning on the Hebrides archipelago, off the northwestern edge of Scotland. A barren chain of islands so exposed, so stripped of resources, that trees cannot even take root in the soil. And yet, people not only survived here, they built homes that stood for generations. Homes that modern engineers, when they first studied them, could not fully explain. No architect designed them. No university trained the builders. Just accumulated knowledge, passed hand to hand across centuries of storms. So how did a civilization with no timber, no mortar, and no blueprint engineer one of the most thermally intelligent structures ever built by human hands? By the end of this, you won't just know the answer. You'll question everything you thought you knew about shelter, warmth, and what it truly means to build a home. The first problem was the most fundamental. To build a shelter, you need wood. But on the Hebrides, there were no trees. Not a single one. The wind from the Atlantic was so relentless, so merciless, that nothing taller than knee-height could survive in the soil. For any other civilization, this would have been the end of the story. But the Scots looked at the ocean, the same ocean that was trying to kill them, and saw something different. They saw a delivery system. Every year, the Gulf Stream carried timber across nearly 3,000 miles of open Atlantic, pulling pine and spruce from the forests of North America and depositing them, piece by piece, onto the Hebridean shore. Merchant ships lost to storms added to this supply. Shattered masts, heavy floorboards, broken oars, arriving in fragments on the beach like gifts from a violent sea. What followed was not scavenging, it was engineering. The Scots developed a precise classification system for every piece of wood that touched their shore. The heaviest, longest planks, thick floorboards from wrecked vessels, full-length oars, were reserved for the couples, the primary load-bearing rafters of the roof. These required both length and mechanical strength to carry the weight of thatch and stone above. Smaller, irregular fragments, broken handles, split beams, nothing was discarded. They were repurposed as joining pegs, secondary bracing, and internal supports. But there was a hidden advantage no one planned for. Wood submerged in seawater for months undergoes a natural chemical transformation. The salt penetrates deep into the fiber, making the timber resistant to fungi, termites, and rot. In a climate where humidity rarely drops below 80%, this was not a minor benefit. Salt-soaked driftwood, it turns out, outlasts freshly cut timber by decades. The ocean had pre-treated their building material for them. The same force that stripped the island bare was slowly stocking its lumber yard. But a roof frame means nothing without walls to hold it. And here is where the Scots made a decision that, to a modern builder, looks like madness. They built their walls without a single drop of mortar. No cement, no binding agent of any kind. Just stone, stacked on stone, with nothing holding them together but geometry, weight, and centuries of inherited judgment. This technique, known as dry stone construction, was not a compromise born from lack of resources. It was a calculated structural choice, rooted in a principle that modern engineers call ductility. Rigid walls crack. A mortar-bound wall, when a force 10 Atlantic hurricane drives into it, has nowhere to go. The pressure builds until something fractures. But a dry stone wall, built from carefully selected flat slabs with maximum surface contact, can absorb that energy differently. It shifts. It vibrates. It moves with the storm rather than against it, dissipating kinetic energy through thousands of micro-adjustments between stones. The wall did not fight the wind. It negotiated with it. But the real intelligence was hidden inside the wall itself. These walls were not solid. They were built as two parallel stone shells, an outer skin and an inner skin, separated by a gap of roughly 30 to 40 centimeters. This gap, called the intramural space, was packed with whatever organic material the island could provide: peat, mud, moss, sometimes compacted household waste. This core served two functions simultaneously. First, it acted as a moisture barrier. When Atlantic rain drove into the outer stone layer, The peat and mud absorbed it like a sponge, preventing water from ever reaching the interior living space. Second, the stones in both shells were tilted at a slight outward angle, ensuring that any water penetrating the wall was pulled downward and outward by gravity, away from the home's center. And then there was the thermal mass. Stone and peat, combined in this density and thickness, walls measuring 1.5 to 2 meters at the base, absorb heat slowly and release it even more slowly. During the long Hebridean winter, the thick wall became a battery. It collected warmth from the central fire and the body heat of livestock throughout the day, then radiated it steadily back into the living space through the night, long after the fire had dimmed. Modern insulated walls regulate temperature. The Blackhouse wall stored it. No architect drew this, no engineer calculated the ratios, and yet the physics works, precisely, elegantly, and completely. But a wall, no matter how intelligent, is only half a fortress. The other half sat above it, and solving that problem required a different kind of genius entirely. Every roof has one fatal weakness: the eaves. The overhanging edge where the roof line meets the wall is where wind finds its grip. In a storm powerful enough to capsize ships, a flat-edged roof becomes a sail. The wind slides up the wall, catches the overhang, and tears the entire structure skyward. This is not a rare event on the Hebrides. This is every winter. The Scots solved it with a technique so counterintuitive that engineers who first encountered it assumed it was a mistake. They didn't extend the roof to the edge of the wall. They pulled it inward. The roof frame was set back onto the inner stone shell, leaving the full width of the outer wall, up to 2 meters, exposed as a flat ledge above the storm. This ledge, called the topta, functioned as a pressure trap. When hurricane-force wind drove up the exterior wall and hit the topta, it was forced to make a sharp upward turn, jumping over the roof rather than lifting it. The eaves were never exposed. The wind never found its grip. This principle, redirecting airflow rather than resisting it, is the same fundamental logic used in modern aerodynamic design. The Scots arrived at it not through calculation, but through generations of watching roofs fail and roofs survive. The shape of the roof itself completed the defense. Rather than a standard pitched roof with 2 flat faces and 4 sharp corners, the Blackhouse used a hip design, sloping on all 4 sides, with corners that were deliberately rounded. Sharp corners create vortexes, pockets of swirling low pressure that pull stones apart from the outside. By rounding every corner, the builders eliminated these vortexes entirely, allowing wind to flow around the structure like water around a stone in a river. And then the roof was tied down. Not with nails. Iron nails, rigid and inflexible, would snap under the oscillating stress of a sustained Atlantic storm. Instead, the thatch was secured with a web of hand-woven ropes called shugan ion, typically braided from heather or straw. Horizontal anchor ropes, the mather shiomane, ran across the roof at roughly 75-centimeter intervals. Diagonal ropes called fiaragan connected them into a net, and at the ends of every rope, rather than fixing them to the wall, the builders tied large stones and left them hanging freely over the edge. This created something no rigid system could replicate: a dynamic, self-adjusting tether. When the wind pressed down on one section of roof, the hanging stones on the opposite side pulled tighter. When the storm shifted direction, the entire system redistributed its tension automatically. The roof didn't resist the storm. It breathed with it, flexing, adjusting, absorbing, held down not by rigidity, but by the constant, patient pull of gravity. These ropes weren't just holding a roof together, they were holding a family's entire world together. The shell was complete. Stone walls that negotiated with wind, a roof that redirected force rather than absorbing it, a structure that moved when it had to and held when it mattered. But an empty shell doesn't keep you alive. What happened inside the Blackhouse was where the true depth of this civilization's intelligence revealed itself. Because the Scots didn't just build a structure to block the cold. They built a living thermal system, one that ran on biology, chemistry, and a philosophy of waste so radical it makes modern sustainability look like an afterthought. It began with the cattle. In most cultures throughout history, humans and livestock were separated. The animal space was outside, or at best adjacent. On the Hebrides, that separation was a luxury no one could afford. Highland cattle were housed at the lower end of the Blackhouse interior, a section called the thatch. built on a slight incline so that waste drained naturally through floor trenches. But their presence served a purpose far beyond convenience. A single adult cow generates approximately 100 watts of continuous metabolic heat. In a blackhouse containing 5 to 10 cattle, that biological output, somewhere between 500 and 1,000 watts of steady, silent warmth, could maintain the interior temperature 5 to 10 degrees Celsius above the outside environment, even with no fire burning. Modern households spend an average of $1,500 to $2,000 per year on heating. The Blackhouse heated itself for free every night, powered by animals that also produced milk, wool, and eventually meat. They didn't fight the cold. They recruited it into the system. At the center of the human living space sat the cagel, a peat fire, burning directly on the earthen floor. And above it, nothing. No chimney, no flue, no opening in the roof to let the smoke escape. To a modern observer, this looks like an oversight. It was the opposite. In a house with a chimney, warm air rises and exits through the flue, and in doing so, pulls cold replacement air in through every gap and crack in the structure. This stack effect can account for the loss of up to 50% of a home's generated heat. By eliminating the chimney entirely, the Scots closed that loop. The smoke rose, accumulated beneath the roof in a warm cushion of heated air, and slowly permeated outward through the porous thatch, taking almost no useful heat with it. The interior stayed warm, the thatch stayed preserved, and the smoke itself became something far more valuable than anyone outside the Hebrides would have expected. But what they did with that smoke next, suspended in the rafters, in the darkness above the fire, is something no refrigerator engineer would ever think of. The rafters of a blackhouse were never empty. Suspended in the darkness above the fire, in that permanent layer of slow-moving peat smoke, hung the family's entire food supply for the year. Salmon, cured meat, and most significantly, the guga. Once a year, specialized hunting teams from the village of Ness made the dangerous open water crossing to a remote rocky outcrop called Sula Skair, located approximately 40 miles north of the Hebridean coast. There, they harvested young gannets, salted them immediately in heavy brine to begin preservation, and transported them back to the blackhouse rafters for cold smoking. What followed was a precise biological process. Peat smoke, maintained at a temperature range believed to be between 20 and 28 degrees Celsius, penetrated the surface of the meat over a period of approximately 20 hours. At this thermal range, low enough that the protein fibers remained uncooked, high enough that bacterial growth was suppressed, the smoke particles acted as a preservation shield. The phenols and aldehydes naturally present in peat smoke bonded to the surface of the meat, creating a chemical barrier against microbial decay. The result was food that remained shelf-stable for an entire year, without refrigeration, without electricity, without any technology invented after the Bronze Age. The ceiling wasn't architecture. It was a pantry, a smokehouse, and a preservation laboratory, all running silently, continuously, powered by nothing but a fire that was never allowed to go out. But the smoke cycle did not end at the rafters. Every spring, the old thatch, by then saturated with soot, nitrogen compounds, and the residue of a full year of peat combustion, was stripped from the roof. This material, rich in nutrients accumulated through months of slow smoke absorption, was spread directly onto the island's cereal fields as fertilizer. The fields produced grain, the grain produced straw. The straw became the new thatch, a perfect closed loop, roof to field to harvest to roof, requiring no external input, generating no waste, sustained entirely by the island's own biological and atmospheric cycles. And inside that same blackhouse, another form of material intelligence was being practiced at the loom. Harris tweed, today sold in London and Paris for $800 to $1,200 per tailored suit, began not as luxury, but as survival chemistry. The final stage of tweed production was walking, a manual process in which woven cloth was rhythmically beaten against a wooden board by groups of women, to the beat of Oren Louis, working songs whose rhythm ensured the fabric was compressed uniformly. The chemical agent used to strip excess lanolin from the wool and fix the dyes was maestir, aged human urine, rich in ammonia. The dyes themselves came entirely from the island's chemical landscape. Crotal lichen, scraped from salt-sprayed sea rocks, produced deep reddish brown. Native heather yielded dark forest green. Wild iris roots were processed into shades of gray. Soot from the central fire created the characteristic bog-brown tones of Atlantic marshland. No synthetic chemicals, no imported dyes, no industrial machinery. Just the island, its rocks, its plants, its fire, its people, producing one of the most technically sophisticated textiles in human history. Zero waste wasn't a modern environmental philosophy for these people. It was the only condition under which survival was possible. And yet, every material system, no matter how complete, eventually reaches its limit. Every loop, no matter how elegant, needs a center point to hold it together. On the Hebrides, that center point was not a person. It was not a structure. It was a fire. And what they did with it every single night before sleep reveals something about this civilization that no engineering analysis can fully capture. Every night, before the last person in the Blackhouse went to sleep, the same ritual was performed. The woman of the house knelt beside the cajal, the central peat fire that had burned without interruption through every storm, every winter, every generation, and began to arrange the embers with her hands. She divided the glowing coals into 3 equal sections, each one representing a point of protection. In the Christian tradition, the Father, the Son, and the Holy Spirit. In older belief systems, the ancient guardian forces of land, sea, and sky. Then she covered the entire arrangement in a thick, carefully placed layer of ash, not to extinguish the fire, to preserve it. This ritual, called smurad and tena, the smoring of the fire, ensured that beneath the ash, the embers continued to breathe, slowly, silently, invisibly. Through the darkest hours of the Atlantic night, the fire held its heat, waiting for morning. In a world before matches, before lighters, before any reliable way to restart a flame in a wet, wind-battered island environment, an extinguished fire was not an inconvenience. It could be a death sentence. But the smoring was never only about survival temperature. In a civilization with no written records, no books, no formal institutions to carry memory forward, the fire was the continuity. It connected the woman performing the ritual tonight to her mother, who performed it before her, and her mother's mother before that, an unbroken thread of warmth running backward through centuries of storms. The fire was the home's soul, and the soul was never allowed to go out. So return now to where we began, a barren archipelago, force 10 winds, no timber, no mortar, no blueprint, and ask again, how did they survive? Not by conquering their environment, not by importing what they lacked, or engineering around their limitations with outside resources. They survived by reading their world with extraordinary precision, understanding the chemistry of salt-soaked wood, the physics of stone flexibility, the biology of bovine heat, the mathematics of smoke and thatch and nutrient cycles, and building a system so complete, so elegantly closed, that almost nothing was wasted and almost nothing was needed from beyond the horizon. We have replaced peat fires with central heating. We have replaced dry stone with reinforced concrete. We have replaced thatch with weatherproof steel. And our homes are warmer, faster to build, and easier to maintain. But are they more intelligent? The Blackhouse wasn't just a shelter. It was a philosophy made of stone, smoke, and salt. Built by people who understood, in a way we are only beginning to remember, that the most sophisticated engineering doesn't overpower its environment. It listens to it.